when we're called on to calculate what's called an expected value, what we're the best way to describe it, or an expression that describes it a little bit, it's a long haul average. It's an average for the long haul. For, say we could do something for an amount of time, extended amount of time, or extended number, like you flip a coin, but we're talking about flipping a coin hundreds and hundreds of times, if you will. That's what we mean by this, a long haul average. In other words, not just an average for a couple of times. It's doing it for the long haul. Best way to describe it. Okay. All right, now, just some terminology here. Actually, what we're going to do is, the best way to do these is to set up one of those probability distributions. And that's the easiest way to calculate what's called the expected value. So let me just give you, I'm just making these up, so I made them up earlier. So remember on the probability distributions, you list all the x's possible, and then their probability. So the probability of 2, we're going to say that's 1/5, 3, that's 1/5, and 4, that's going to be 3/5 probability. So that's just a probability distribution. So the expected value of x, so we're doing an expected value of a quantity here. So in this case, we're doing it of this x here. So the expected value is, probably good thing here. We're calling expected value E parentheses x. That's the way we notate that. But what it is, it's just the sum of all the x times p of x's. So what I'm going to do on this probability distribution is I'm going to multiply each x times its p of x. So in this particular case, E of x equals x times p of x. So I'm going to do 2 times 1/5. Then I'm going to do 3 times 1/5. Then I'm going to do 4 times 3/5. I'm going to add those together. And that's going to be what is called the expected value of x. Now, if you've got fractions, usually if you leave them as fractions, again, they work out pretty good here. 2 times 1/5, so that's, again, 2 over 1. So in multiplying, you just multiply across, so that's 2/5. 3 times 1/5 is 3/5. 4 times 3/5 would be 12/5. And that's what I'm saying. Usually if you leave the denominators, well, those don't reduce anyway. What do we got there? 19/5. Or 17/5, sorry. Now, so for this scenario here, the expected value of x is 17/5, which is, if we round it or make it a decimal, what was that? 3.4. And so one thing you might note there, is there a question on that? One thing you might note there is this number is bigger than 1. So we're not talking about, it's not a probability anymore, since we're multiplying, numbers times the probability. It's not going to be a probability anymore. So the numbers can be bigger than 1, less than 1, less than 0. You can get some even negative. the negative values. So anyway, that's how you compute it. And we'll do a couple of examples here and then talk about kind of what it means. But is that okay? Any questions on what we're talking about there? Okay, so the big deal is going to be coming up with this table, as you know, so that we can calculate this expected value. Of course, this has a lot of tie into games. And that's the first couple examples anyway I've got. All right, so let's say I've got 2 coins being flipped. You win, the player wins $5 if both are heads. But loses $2 if they are not both heads. So the question is then, what is the expected value of the winnings? Or just expected winnings, another way to put it. But it is an expected value, and so computing here. Well, like I said, again, first step on these is let's make the probability distribution of the x p of x table here for our scenario. So in this case, what does my x represent? Because that's the first thing you need to establish here. What does the x represent in this table? Well, I'm talking about flipping 2 coins, but that, since I'm wanting the expected value of the winnings, I want x to be the winnings. Makes sense, right? So what I want to list under x is all the possible values that we could win, or in this case, lose. There's only 2. We could win $5, or we could lose $2. So let's call that -2. Right? That's what we could win here. So x being the winnings, x could be 5, or x could be -2. Now, next to those then, what's the probability of each of those? Well, the probability that we win $5 is the probability that both are heads. So again, we might want to list out, all the potential possibilities here. There's 4 of them. And so the only way to win $5 is both are heads. So 1 out of 4 is when we're going to win. How much we're going to win $5? 1/4 probability there. Because this is the probability both are heads. Probability to win $5 is the probability both of them are heads. Then, of course, losing $2, well, we're going to lose $2. All the other possibilities there, right? 3 of the 4. We're going to lose $2 3 of the 4 times. 3 out of 4 times. So we're okay here. See where we get that. Okay? So, then, second step is compute the expected value. So, how do we do the expected value? Well, that's why I did this example over here. The expected value is just the sum of all the x times p of x's, and this one's actually a little shorter because now we only have 2 of them. 5 times 1/4 plus Negative 2 times 3/4. You're just going to multiply those two together. Of course, that's just 5/4, and that's minus 6/4. Ah, 5/4 minus 6/4 is negative 1/4, or negative 0.25. Maybe even a better way to write that. Okay? Now, let's think about a little bit what that means. All right, so what we've come up with here is our expected winnings. Now, we can only lose $2 or win $5. We're never going to lose, this is a quarter, right? $0.25. That's what that is. We're never going to lose $0.25. So that's why we're saying what this comes up with is a long haul average. In other words, if we played this game hundreds, thousands of times, we would expect to average losing 25 cents every time we play. So if we played 100 times, we'd lose 25 cents every time. We lost $25. Okay, that's what we expect. Expect to average on winnings. So in this case, obviously, the game does not favor the player here, does it? Because you're expected to win negative dollars. Negative, well, not quite a dollar, but negative amount, a negative amount. So anyway, that's what this means. It's an expected average, long haul average. Okay. Let's say, here's number 2. Again, a game type problem. Okay, so let's say we play a game. Let's roll a die. Just a single, okay? All right. Okay, yeah, let's. If all right, you win $10 or 5, $20 or 6. So if you roll the big numbers, you get big money. But nothing if you roll any other number. Okay? All right. So let's do this one in 2 parts. Okay, so what is the what is the expected winnings here? Well, here's our table here. Again, X is the winnings. All right, so what are the potential winnings here? You tell me.
0.
0, yeah, I could win nothing. If I roll, what, 1, 2, 3, or 4, I get nothing. So what's the probability of that then? 1, 2, 3, yeah, 4 out of 6, I'm winning 0. Could win 10. If I roll a 5, I win 10. So probability of that, there's only 1 out of 6 chance of that happening, right? And then I could win 20. 20 if I roll a 6, and so that's 1 out of 6 chance of that happening too. Is this okay? Sound all right? We there? So, the expected winnings then, we multiply each x times p of x, 0 times 4 over 6, plus 10 times 1 over 6, plus 20 times 1 over 6. Well, of course, 0 times anything is 0, so you got 10 over 6, plus 20 over 6, if we just write them, again, multiply them. Numerators and denominators there. 30 out of 6, or 30 over 6, which is 5. So that's a little better game here, obviously, because, well, as it's set up here, there isn't any time I lose money, okay? But that's where the second part of the question is going to come. All right, so it's a $5 expected winnings. Now, I never win $5, but because of the way it works, you know, more often than not, I win 0. Sometimes I win 10, sometimes I win 20. So the expected winnings turns out to be $5. Okay, now, here's the other thing they'll maybe ask about, and that is a fair game. Well, number 2, what would be a fair price to play this game? What would be a fair price to play this game? Well, mathematically speaking, a fair game is where the expected winnings is 0. So if it balances flat out, you don't have any expected winnings, again, it's a long haul average, so the player expected average is winning nothing, but not losing anything either, so it's right in the balanced middle there. That's what we mean by a fair game. So the question was, what would be a fair price to play this game? Well, if the expected winnings without a price is $5, wouldn't the fair price be $5? That would make it 0 out. So the fair price here would be $5. I mean, if we charged $4, well, the expected winnings is still in favor. You'd have a $1 expected winnings. So anyway, if it asks about a fair price, that's just what makes the game come out expected value 0. Any questions about that? All right. Okay. I got one more here.